Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 173 derived the mass moments of inertia for the homogeneous right circular cone shown with respect to the x, y, and z axis. So here's the figure and the orientation of the cone. So the radius is denoted here with r and the height which is along the x-axis is h. So for our solution, let's have an elemental shape which is a circular plate as shown. The radius is denoted by ry which is equal to rz which is simply equal to y. So the distance of the plane of this circular plate from the vertex is or vortex is x, and the thickness is dx shown. The radius is ry, which is simply y, which is equal to z because this is a circular plate, and our guide is we have the y-axis through the centroid of this element and the y prime axis and the centroidal z prime axis as shown. So since x-axis is perpendicular to the plane of this circular plate and through the center of gravity, our guide is differential ix, which is differential ix prime also, and it is equal to density times thickness times polar moment of inertia of area polar moment of inertia of area with respect to the x prime axis or the x-axis in this case. So the thickness is dx and the polar moment of inertia of area is simply pi ry to the fourth over 2 because it is supposedly times 2 of the moment of inertia of area with respect to the y-axis. And since Iy equals Iz by symmetry of this circular plate here, that's why it is pi ry to the fourth over 2. So differential Ix is rho dx pi over 2 ry quantity to the fourth. Then by take note that ry equals rz, which is simply just y. So ry equals y equals z. So by similar triangles, we have y as to x equals r as to h. So differential Ix is density times dx pi over 2 y to the fourth. Then by similar triangles, y as to x equals r as to h. Therefore, y is r over h times x. Substitute into this equation. So Ix equals pi over 2 density integral from 0 to h of y to the fourth, and y is r over h x quantity to the fourth dx. Simplifying and putting the constants before the integral sign, and take note that integral of x to the fourth dx is x to the 5 over 5. So Ix equals density pi over 2r to the fourth over h to the fourth times x to the fifth or y x to the fifth over 5 from 0 to h. So substituting, Ix is density times pi over 10 r to the fourth over h to the fourth times h to the fifth. So we can cancel h to the fourth here, leaving 1h here. And take note that the volume of the cone is, right circular cone is pi over 3 r square h. So let's have density times volume pi over 3 r square h. So that what's left would be 3 tenths r square. And noting that density times pi over 3 r square h is mass. So Ix equals density pi r square h over 3 times 3 tenths of r square. So take note that this is the mass of the cone, density times volume of the cone. Therefore, Ix is 3/10 mass r square. So that's the moment of inertia, mass moment of inertia with respect to the x-axis of this cone and oriented in that manner. So Ix equals 3/10 mr square. So likewise, differential Iy, which is equal to differential Iz, Iy equals Iz, and it is equal to differential Iy prime plus differential mass distance square, which is x square in that case. So Iy equals Iz, and differential Iy equals differential Iy prime plus differential mass x square by parallel axis theorem. So differential Iy prime, on the other hand, is density times thickness, rho times dx from the preceding experience we have on this element, circular plate. So differential Iy equals density dx times pi ry to the fourth over 4. That's the moment of inertia of area, which is area of a circle with respect to the y prime axis. Then differential mass is density times differential volume of the circular plate, and the volume of the circular plate is pi radius square dx. Ry is again y, which is equal to z. Take note of that. And we replace ry by y and y by r over hx. So differential Iy equals then pi over 4 density r over h x to the 4 dx plus density pi r over h x square d times x square dx. So take note that integrating, this is integral of x to the 4th dx, and this is also integral of x to the 4th dx. Integral is x to the 5 over 5. So Iy equals density pi over 4 r to the 4th over h to the 4th times quantity x to the 5th over 5, then plus from 0 to h plus density pi r square over h square x to the 5th over 5 from 0 to h also. So simplifying, Iy equals density pi over 4 r to the 4th times pi over 20, rather 4 times 5 is 20, r to the 4th over h to the 4th, then we have h to the 5th, and density pi r square over h square, then this is also h to the 5th, x to the 5, or 0 from 0 to h, or h to the 5th. Then this is Iy equals density pi r square over 3h. This is the volume of the cone. Then what remains in the first term is 320 of r square. Then for the second part, after factoring out density pi r square h over 3, what is left is 3/5 h square. Then 3 over 5 is common to these coefficients inside this parenthesis. And take note that this is the mass. So factoring out 3/5, so Iz equals Iy equals 3/5 of mass times 4 r square over 4 plus h square. So that's it. That's it. Iy equals Iz equals 3/5 of mass of the circular right circular cone times r square over 4 plus h square. So I hope that you were able to follow the solutions and the principle here, especially in setting up the differential moment of inertia, mass moment of inertia, is based on the principle on mass moment of inertia of a circular plate. Level 174, derive the mass moments of inertia for the homogeneous solid sphere shown with respect to the x, y, and z axis. So I'll present two solutions, and by symmetry, Ix equals Iy equals Iz. So for the first solution, I'll consider a cylindrical shell as element so that the direct formula for mass moment inertia can be established, and that is equal to uh, radius of gyration square or constant distance square times differential mass. So we have to consider this cylindrical shell element. The radius is y, which is equal to z. The thickness is along y, so dy, and the length is this circular end is on the yz plane, so the length is just x because it is along the x-axis. And this lies in one right half of the sphere, so we have to multiply the value by 2. So that's dy, and the length is x. So ix equals iy equals iz by symmetry, and ix is equal to distance square or radius of gyration square, which is in this case the radius of the cylindrical shell, y square, the constant distance from the axis to the element of the shell, which is this rectangular strip here, and the radius or distance is y square and the length is x, and the differential volume of the cylindrical shell is either area of the annular ring, which is circumference times thickness. Circumference is 2 pi y, 2 pi times radius. Thickness is dy, and the length is x. So that's the differential volume. So Ix equals 2 times integral 0 to a of radius of gyration square y square, differential volume. So again, the reason why we had to multiply it by 2 because in this strip we consider only the right half, and that's why we multiply it by 2 to get the entire mass moment of inertia of this sphere. So y square, density times volume. The volume is circumference of the cylindrical shell, which is this 2 pi y. The thickness is dy and the length is x. Another way is if we apply uh, we call this Pappus theorem, which is area of the rectangular strip times distance traveled by the centroid of that strip. That's the differential volume. So let's concentrate on this volume. This rectangular strip, which is clear when we have to consider the quarter circle on this part here. The length, the area of the rectangular strip is length x times dy. So we have x dy here. And if that rectangular strip is revolved about the x-axis, it generates the circumference. That's the distance traveled by the centroid of that rectangular strip, which is 2 pi y. So we have 2 pi y. So it's the same thing. So to make it clear, Ix equals, so simplifying 4 pi rho integral of y cubed times x dy. Now, what's the relationship between x and y? So let's now reveal it here. So this is the circular part, which is here in this quadrant, and this is the length of the strip, which I told you, which is x. That's the rectangular strip x, and the thickness is dy, and the radius or distance of the centroid of this rectangular strip from the x-axis, which is here, is y. So if we express the differential volume of the cylindrical shell as area of the strip, rectangular strip, which is x dy times distance traveled by the centroid is here, and if it is revolved about the x-axis, one revolution, the distance traveled would be 2 pi y. So it's the same thing. It's the same as annular area. The annular area is circumference 2 pi y, and the thickness is dy, 2 pi y dy, and the length is x. And we have to multiply it by 2. So from this figure, although the standard equation of a circle is supposedly x squared plus y squared equals radius squared if the center is at the origin, but I'll just use Pythagoras theorem here, which is the same as x squared plus y squared equals a squared. So therefore, because the variable of integration here is y, we express x as square root of a squared minus y squared. So Ix is 4 pi times density integral 0 to a of y cubed times square root of a squared minus y squared times dy. And you already experienced this type of integral in the preceding topics in statics, especially on centroids, and this is by trigonometric substitution. So we put y equals constant sine of theta because the integrand involves a squared minus y squared. Differential y is a cosine theta differential theta. And for the limits, when y is 0, 0 over a is 0, arc sine of 0 is 0, so it's still 0. For the upper limit, when y is a over a is 1, and arc sine of 1 is pi over 2. So we then use Wallay formula again. So Ix is, we have to show the right triangle here. So this is theta. Sine theta is opposite to y hypotenuse a. And this is square root of a squared minus y squared, which is in terms of a and theta, a cosine theta. So Ix equals 4 pi density, integral from 0 to pi over 2 this time, we change limits. Y is a sine theta quantity cubed, then a cosine theta, then times dy a cosine theta differential theta. So Ix is 4 pi density times a to the 5 integral from 0 to pi over 2 of sine cubed theta times cosine squared theta differential theta. So by Wallay formula, take note that the power of sine and cosine are not all even, so therefore the value of alpha in the Wallay formula would be 1. So remember the rule, first decreasing by 2 until 1 or 2. So 3 minus 1 is 2, so stop. Then 2 minus 1 is 3 minus 1 is 2, stop. For cosine, 2 minus 1 is 1, then we stop. Alpha is 1, all over sum of powers 5 decreasing by 2, so 5 times 3 times 1 in the denominator. So Ix is 4 pi rho a to the 5 times 2 times 1 times 1 over 5 times 3 times 1. And if you simplify that, that's 8 over 15. So Ix is rho times 8 over 15 pi a to the 5th. The volume of the sphere is 4/3 pi a cubed. So let's have that. Ix equals density times 4/3 pi a cubed. Then what is left is 2/5 a squared to make it 8 over 15 pi a to the 5th times density. So remember that density times volume is mass of the sphere. Therefore, if this is mass, then Ix equals Iy equals Iz is 2/5 ma squared. So that's the mass moment of inertia of a sphere with respect to the axis, centroidal axis. So 2/5 ma squared. Ix equals Iy equals Iz. Then for our second solution, you might not like this solution. Then we use the element in the preceding examples. So imagine that this element is a circular plate this time. This is no longer annular area. This is a circular plate of radius y, and the centroidal y prime axis there, centroidal z prime axis is here, and the distance from the yz plane is x. And the thickness is this time dx. So differential Iy over 2 equals differential Iy prime plus differential mass x squared. This is transfer formula. And it is only half because we only consider the right half. And again, the element is a circular plate of thickness dx this time. So therefore, differential Iy is 2 times differential Iy prime is rho times thickness, remember? Then moment of inertia with respect to the centroidal y prime axis, which is pi over 4 radius to the fourth, and radius is y. Then plus differential mass density times volume of this circular plate is pi radius square pi y square, and the thickness is dx, remember from the preceding slides and before, or examples, preceding examples and before. So pi radius square dx, that's the differential volume of the circular plate. Distance between y prime axis, so this is the y prime axis, and the y axis is x. So that's why you have x square here. So simplifying Iy equals rho pi over 2 integral 0 to a of y square from this figure is a square minus x square. Since this is y to the fourth, so it's like a square minus x square quantity square. That's y to the fourth because this is y square. Then plus 2 times density times pi, a square minus x square times x square, integral of a square minus x square times x square dx from 0 to a. So before we integrate, let's expand this first. So Iy equals rho pi over 2 integral 0 to a of quantity a to the fourth minus 2a square x square plus x to the fourth dx. And this is 2 density times pi. We can evaluate the integral of this, times a square x cube over 3 minus x to the fifth over 5 from 0 to a. So we can evaluate that. A to the 5 over 3 minus a to the 5 over 5, that's 2 over 15. A to the 5 times 2, so that's 4 over 15 a to the 5, then times density times pi. Likewise, this one is rho pi over 2 quantity a to the fourth x minus 2/3 a square x cubed plus x to the 5 over 5 from 0 to a. So it's like a to the 5 minus 2/3 a to the 5 plus a to the 5 over 5 minus 0. And this is density pi 4 over 15 a to the 5. Likewise, this one is also, so rho pi divide by 2, so 4 over 15 a to the 5 plus rho pi 4 over 15 a to the 5. Adding, that would be 8 over 15 density times 8 over 15 a to the 5, which is the same as this. And therefore, we will arrive at the same final results, that Ix equals Iy equals Iz equals 2/5 ma square. So Iy equals density times 8 over 15 pi a to the 5th, which is the same as this. So we arrive at this same answer. So that's it. And I hope that you can remember the mass moments of inertia of the common figures before attempting to consider other different figures.